All right, let's talk about two words we all kind of throw around interchangeably: temperature and thermal energy. But they're actually fundamentally different. And getting this difference down is, well, it's the key to understanding a whole lot about how the world works. And we're going to figure it all out with a super simple story about a bowl of soup.
So here's the puzzle at the heart of all this. It really does sound like a riddle, doesn't it? Imagine this. You've got two bowls of the same exact soup. You pop in identical ice cubes, but one ends up perfect and the other one gets cold. How on earth is that possible? Stick with me, because the answer, believe it or not, is surprisingly simple. Okay, so to get to the bottom of this, let's really set the scene. Let's call it a tale of two soups.
So, picture this. You've got this big pot of soup bubbling away on the stove. You pour a nice big serving into a bowl for yourself, and then a smaller portion into a mug for, say, your little brother. Both of them are steaming, way too hot to eat right away. So what do? You grab two identical ice cubes from the freezer and plop one into each.
Okay, a minute goes by, you take a spoonful of your soup, and it's perfect. Just the right temperature, not scorching at all. But then your brother takes a sip from his mug, and he's like, hey, this is cold. And he's totally right. It's actually gotten cold. So what in the world just happened? We had the same soup, same starting heat, the same exact ice cube, but completely different results. This is our mystery. To crack this case, we've got to get our definitions straight. Let's start with the big one, the one we think we all know. What actually is temperature?
Okay, the single most important word on this slide is average. Seriously, temperature is just a measure of the average kinetic energy of all the molecules in something. You can basically think of it as the average speed of all those tiny little particles zipping and bouncing around in the soup. It's not the total energy, not at all. It's just the average for any given molecule.
So let's bring this back to our soup. Since you poured both the bowl and the mug from the exact same pot, the molecules in both soups had the same average speed. And this part is absolutely crucial. That means they both started out at the exact same temperature. No difference there.
Okay, so if the temperature was the same, well then that can't be the whole story, right? Something else has to be going on. It's time to introduce the real secret ingredient to solving this mystery: thermal energy.
And here it is, the key difference. If temperature is the average, thermal energy is the total. It's not about the speed of one typical molecule anymore, it's the grand total, the sum of all the energy from every single molecule in that soup, all added up together.
It's simple, really. Your big bowl just has more soup in it than the small mug, and more soup means more molecules. Since thermal energy is the total energy of all those molecules, well, more molecules means you've got way more total thermal energy. Simple as that. So let's update our little scorecard here. They both started at the same temperature, yes, but their thermal energy? Totally different, right from the get-go. Your big bowl was like a savings account with a ton of energy stored up. Your brother's little mug? It was more like having just a little bit of pocket change.
All right, we've got our two key ideas on the table: average energy, which is temperature, and total energy, which is thermal energy. We have everything we need now. Let's finally solve this soup mystery.
Okay, here's exactly how it went down. To melt, an ice cube needs to draw energy from the soup. Think of it like a bill that needs to be paid. Since the ice cubes were identical, they both demanded the exact same energy payment. Now the little mug, with its pocket change energy reserve, it paid the bill, but doing so took a huge chunk of its total energy. That's why its average energy, its temperature, took a nosedive. Your big bowl, on the other hand, with its massive energy bank account, it paid the exact same bill, but for the bowl, it was just a tiny withdrawal. It barely made a dent, so its temperature only dropped by a little bit.
And this whole idea doesn't just work for soup. This applies to, well, pretty much everything. So to really make sure this concept sticks, let's move beyond the bowl and try out a couple more quick thought experiments.
Okay, let's switch things up. What if you took that little mug of soup and zapped it in the microwave until it was absolutely scorching hot, way, way hotter than your big, just warm bowl? Now, which one do you think has more thermal energy?
And this is where it gets really interesting. Even though that mug is way hotter, meaning its molecules have a higher average energy, your cooler, bigger bowl probably still has more total thermal energy. And why? Simple. It just has so many more molecules. It's a perfect example of how a huge army of slow-moving things can have more total energy than a tiny group of super fast things.
All right, one last example. Let's say you get a phone call, you get distracted, and you just leave your bowl of soup on the counter. You come back an hour later, and it's cooled down to room temperature. We've all seen this happen. But stop and think for a second. Where did all that energy go?
Well, it transferred into the air in the room. The soup lost a huge chunk of its thermal energy, so its temperature dropped a lot. But the room itself, it doesn't feel any warmer, does it? Nope. That's because the air in your room has trillions upon trillions more molecules than your little bowl of soup. The thermal energy of the room is like an entire ocean. The energy that left your soup, that's like adding a single drop of warm water to it. It makes absolutely no difference to the overall average.
So, when you boil it all down, what's the one big takeaway here? The whole thing, everything we've talked about, hinges on one simple but incredibly powerful difference: total versus average.
Just remember, temperature is the average energy. It's like asking about the speed of a single, typical molecule. But thermal energy, that's the total. It's the combined power of all the molecules working together. That's it. That's the core difference. And it explains everything from our little soup mystery to why the entire ocean doesn't boil on a super hot day.
So, I'm going to leave you with one last question to chew on. Think about a lit match. It has a crazy high temperature, right? Thousands of degrees. Now think about a giant iceberg, which is obviously freezing cold. Which one has more total thermal energy? I think, based on everything we've just gone over, you know the answer. Thanks for joining me.